Myself, Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today, in this session of graph theory, we are going to deal with factorization. We are familiar with the factorization of numbers and all. Now, we'll see how we are going to deal with the factorization of graphs and what is meant by the factorization of graph and all. And we'll see some applications of factorization. Actually, the factorization arose from the question of decomposition of graph into edge disjoint spanning subgraphs having particular property pave the way for the development of the branch called factorization of graphs. That is, we have to find if the graph can be partitioned into edge disjoint spanning subgraphs. For that, before going to factorization, we will see some prerequisites for this. Bring sum of two graphs. I hope this how we can write this G1 and G2 are two graphs, then we write this bring sum of graph to be G1 equal to like this, and it is written as G1 bring sum G2 equal to G. This G has a property that vertex set of G means vertex set of G1 union vertex set of G2, and edge set of G means edges of either in G1 or in G2 but both in not in both. There is some operations subgraph, and a subgraph H is said to be a subgraph of G if the vertex set of H is a subset of vertex set of G and edge set of H is a subset of edge set of G. This incidence relation is also followed in it. Then spanning subgraph. A graph is said to be a spanning subgraph of a given graph if the subgraph if it contains all the vertices of the given graph. Subgraph which contains all the vertices of the given graph, it is termed to be a spanning subgraph. And edge disjoint subgraphs. If G1 and G2 are two subgraphs of G, then they are said to be edge disjoint if G1 and G2 doesn't share the same edges of G. And matching. Matching is a subset of edges. What M is said to be matching is a subset of edge set of the given graph and such with the property that not two edges in M are adjacent. And perfect matching means a matching which covers all the vertices, or it is adjacent with matching which covers all the vertices, or match perfect matching we call it as if a matching contains a set of edges which is incident with every vertices of the given graph, then we say that matching is to be perfect, or it saturates every vertices of the given graph, then it is said to be a perfect matching. Matching which saturates every vertices of the given graph, then it is said to be a matching, perfect matching. Now we will see the formal definition of what is a factor of graph and what is factorization of graph. A factor of graph means a spanning subgraph of G. Factor of a graph G means a spanning subgraph of G. If G1, G2, etc. Gm are pairwise edge disjoint subgraphs, that means G1 doesn't have the same edges as that of G2 and same. No one has same set of edges. Pairwise edge disjoint subgraphs of G such that union of all the edges of this GIs, union I equal to 1 to M, E of GI equal to E of G. Then G is said to be factorable or factorized into subgraphs. Okay? If we can find some subgraphs, spanning subgraphs, that means all these subgraphs contains all those vertices of the given graph, and they are edge disjoint spanning subgraphs, and such that the union of these edge disjoint union of the edges of these edge disjoint subgraphs constitute the edges of the given graph, then we say that it is the given graph G is factorable or factorized into factors. And these G1, G2, etc. Gm are known as factors of G. And we express this as G1, G equal to G1 ring sum G2 ring sum etc. Gm. Okay, the expression is also otherwise called factorization of G into G1, G2, etc. Gm. So, okay, I will see that. An R factor of a graph means R regular factor of graph. Means R regular factor means a regular graph means which is a regular graph of degree n by n or something, means every vertices are of degree n. So this R regular graph means R factor means R regular factor means every vertices are of degree r. This when we are factorizing G into G1, G2, etc. and we will be getting edge disjoint subgraph G1, G2, etc. Gm. And this when we are taking each G1, Gi, when we are taking each Gi, every vertices will be of degree r. Then it is called R regular factor, and we call it as a R factor of given graph. If r equal to 1, then R factor is called on factor, and clearly this on factor will be a perfect matching of G. Let's see this in examples. One remark is that if there is a factorization of G into R factors, then G is said to be R factorable. That means if we can decompose G into subgraphs such that it is an R factor or R regular factor. This R regular factors we can decompose, then it is called G is said to be R factorable. Consider this graph. If it is G and this is H1 and H2. Now we are decomposing G into two subgraphs such that with this is only possibilities of decomposing G into two subgraphs, edge disjoint subgraphs. Here look at this H1 and H2. They are edge disjoint subgraphs of G, and this union of the edges of H1 and H2 means union of the edges of H1 and H2 gives this G, and this no. Here we can find that H1 is an R regular factor where R equal to 1. So this is H1 and H2 produce a on factorization of the given graph G. Now consider this graph, which is bipartite graph. Here we can see that we have 6 vertices, and this is K33, right? Because by every vertices on this first partition, every vertices on this first partition is adjacent to every other 3 vertices in the second partition. So it is K33. And we can find that this H1, H2, H3. If we are giving names to all of this, we can find that it is edge disjoint. This is properly edge disjoint. If we are taking 1, 2, 3 and ABC here, we can put like this: 1, 2, 3, ABC here, 1, 2, 3 here, and ABC here. You can see that it is edge disjoint subgraphs. H1, H2, H3 are 3 edge disjoint subgraphs of this given K33. So it's a on factorization of the given graph K33 or the given graph G. Okay. Now we will see some results on factor. If a graph G has a non-factor, graph G has a non-factor, if and only if it has a perfect matching. Now here we have seen that it's a perfect matching. It's a matching because by no two edges are adjacent. And is it a perfect matching? Yeah, because every vertices of the given graph is being saturated, or every vertex of the given graph is up incident with at least one edge. So it is a perfect matching. This is a perfect matching. Then a graph is said to be on factor. A graph has a non-factor if and only if it has a perfect matching. That is, if a graph has one factor, then it is a perfect matching. If a graph has a perfect matching, then it is one factor. Then it can be said to be unfactored, or it can be said to be unfactorized, or it is a one-factor graph. A graph has a non-factor if and only if it has a perfect matching. Every R regular where R is greater than or equal to 1, bipartite graph is unfactorable. Here it's a 3 regular bipartite graph, so it is unfactorable. A complete graph K2P is unfactorable for any positive integer P. We were dealing with KP. If you are writing like this, remember here what it is. It's 2P. If you are taking this KP as a, then for every even P. That is, every complete graph K2P is non-factorable for every positive integer. You can see with this K2 and P, K2, then K4 and all, we can see that it is non-factorable. Now this K6, K6 is shown here. That is equal to K, K2P where P equal to 3, right? So it is K6, and these are the different, when we are factorizing this K6, we will get this 5 factorizations of this K6. Edge disjoint factors of this, these are first, second, third, fourth and fifth. So different edge disjoint. That is, this K6 is unfactorable, or this unfactorization of this K6 is shown with this 5 figures. Actually, it is not, though in some small graphs, we can see that, like that first graph that we consider, this one, it is so easy to find this one factor. And when the order and size of graph is increasing, it is not so easy to find, dictate whether a given graph is unfactorable or not, or whether one factor of the graph exists or not. Some graphs, theorists have shown that many graphs have exactly one factors, and some graphs may not have just exactly one factor center. Some have shown that some particular graphs have exactly one factors. And what type of graphs may have this one factor? We have seen that K2P has one factor. K2P is unfactorable, or it has a non-factor. Now we'll see some cases. Before going to that, first we'll see what is an odd component and even component of a graph. A component of, what is a component? The group, set of vertices, and when they are connected by a path, it forms a component. So graph may have 2 or 3 components, like that. We have dealt with some forest and earlier, and forest graphs with a tree graph with so many tree components. It's called forest. So a component of a graph is said to be even or odd. That is, a particular part of a graph is said to be even or odd if it has even number or odd number of vertices. Even number of vertices, then it is said to be an even component, and if it has odd number of vertices, then it is termed to be an odd component. The number of odd components are usually denoted by number of odd components of G or of G. Usually there is no notation for even components of G. Now consider this graph. This graph G, if it is considered the total, it is a graph, we can say that 1, 2, 3, 4, 5 components are there. And what is the number of odd components? Here we know that it is 2 vertices. Here 5 vertices. Here 4 vertices. Here 3 vertices. Here also 3 vertices. So the number of odd components is 3. Sometimes we may get confused that here we have 2 edges, here we have 3 edges, so this is only the odd component. No. We have to count the number of vertices. If the number of vertices is odd, then we call it as an odd component. So in this graph, if this is a given graph with these 5 components, then the number of odd components is 3. So I have already told that whether a given graph is factorable or not factorable is different. It is not so easy to say, and some of them have started. Most of the many graph theorists have took research on that, and they have given some results on that. And the most significant result on factorization is given by William Thomas Chad, and characterizes the graph have an unfactor, giving necessary and sufficient condition. Conditions, also the conditions for the graphs to have factors were given by mathematician Peterson. I hope you remember the Peterson graph also. Yeah, graph, 3 regular graph with 10 vertices and 15 edges. And we will see what is the Stud's condition, or Stud, what Stud has told whether a given graph is factorable or not. A graph has one factor if and only if number of odd components of G minus S is less than or equal to mod S for every S subset of V of G. Is that we are given a graph G, and if we are finding S subset S of vertex set of G, and if we are removing this, we are deleting all those vertices of the given newly subset S, that is number of, then if you are taking the odd components of that graph, that is the graph, we are given a graph with certain vertices and we are removing certain vertices from that. Then removal of vertices means that it results in the deletion of all the edges incident with that vertex. So if you are removing certain set of vertices, say 3 or 4, and we are removing, then the number of odd components resulting from that G minus S is less than or equal to that cardinality of the given taken set S. This condition is also applicable in the case of perfect matching also. Ted has given this condition in the case of factorization and also in perfect matching. And what Peterson has told is that every 3 regular graph with no cut edges has a 1 factor. Every 3 regular graph means every vertex is of degree 3 and with no cut edges. That is, if we cannot find any edges whose removal disconnects the graph, then that graph has a non-factor. Also, every regular graph with positive even degree has a 2 factor. That is, every regular graph. Regular graph means every vertex is of same degree. With positive even, then what is the condition that not only regular, it is positive even degree. Then it has a 2 factor. And we will see some applications of matching and factorization. We have already seen some Chinese postman problem. That is, a postman starts from a point. He has to go through all the routes and minimum covering the minimum route, and he has to go through all the path that he has to go through, and he has to reach back the starting point in minimum time and minimum distance traveling. That is called what is called Chinese postman problem. We have discussed earlier in our session that it can be solved with the shortest path problem. Later it can be shown that it can be solved by finding a perfect matching of the weighted graph. How this perfect matching means? Now to edges are adjacent, and we can find this. What is perfect matching? Every vertices are being covered. That is, it covers all the points. This every vertices are being covered means to cover all the vertices, he has to go through all the edges. And we have to find a covering of the perfect matching of the given weighted graph. Why this weighted graph? Because when we are marking these edges of a graph with some positive integer, we are assigning a positive value to the edges, then it is termed as a weighted graph. Here we can put the distance between the points to be the weight. So a situation can be termed to a weighted graph. Then finding a perfect matching of the weighted graph also gives the results to the Chinese postman problem. Another application of this on-factorization of graph is scheduling of sports competition. We all know that nowadays we are having this IPL, everything and all. How these matches are being fixed? How not fixed means how the matches are being scheduled, so that how every team can play. This is an application, and here we are applying this on factorization. Okay, how we'll see how this on factorization is being applied for this one. Actually, it is termed as a round-robin tournament. A round-robin tournament. There is a competition among P teams, where P should be greater than or equal to 2, where each team plays with every other team. Suppose 6 teams are there, each teams play with every others. But exactly once. Then we will be taking another knockout and all. From there, we are taking the next part. Okay. Such situation we can represent them as a complete graph on P vertices. If there are P teams, then we can play them as 6. If there are, that is, if there are, let's take 5 teams. A, B, C, D, E. Okay. Then A has to play with, each team has to play with others. Then A will be playing with B, C, D and E. Then B has played with A. So we need not draw any line. Then B has to play with C, D and E. Same way, C, E, C, D, D, E. So what is the result we are getting? It will be a complete graph because every vertex is adjacent to every other vertex. So it's a complete graph. In this situation, if there are 10 teams, we will get a complete graph on 10 vertices. The vertices corresponds to teams and the edge between the vertices represents a match between the corresponding team. If I am having 4 teams, A, B, C, D, if this AD represents A, B, C, D. This represents a match between A and D and also D and A. Okay. So the edges between, here we are not going for any directed lines and all, but just simply putting the lines away. It is expected to complete the tournament in minimum number of days. If one day we are playing this, A and B is playing, then no other matches going on. Will it be like that? If we are taking this, if there are 10 matches, 10 teams, we know that there are n into n minus 1 by 2 edges. So, how much? 45 days can we take like that? No. So, we have to complete the match in minimum number of days. But we all know that efficiency of a game is being maximum number of teams and minimum number of days and that. On conducting a game, it is expected to complete the tournament within a minimum number of days with the condition that each team can play at most one game in a given day. Is it possible that India can play with Australia and Pakistan in the same day? No. India has to play, then we have to, a maximum one match can be played. Right. So with that, we can do like that. It is expected to complete the tournament with minimum number of days with the condition that each team can play at most one match in a day. The matches played in a day can be called a round of the tournament because there will be n into n minus 1 by 2 rounds like that, and we will have to get one match played on a day is called term to be a round of the tournament. At most, this integer modular p by 2 matches can be played in a given day. Why? Because each team, we can have this, if 4 teams are there, either this match will be happening or this match will be happening, else this match will be happening. Anyway, it is 4 by 2, right? So it's this integer modular p by 2 can happen. Why? Because each team can play at most one game per day. This on factorization of KP corresponds to a schedule of tournament in which on factor represents the round with maximum number of matches. Here we have seen this 4 of the 4. We have this different combinations like that. 2 combinations like that. There's of 4 vertices like that. This on factorization. This means corresponds to a schedule of tournament in which each factor represents a round with maximum number of matches. That is p by 2 matches. PC2 factors. PC2 matches. Since Kp has p into p minus 1 by 2 edges, the tournament can be completed in p minus 1 days. We are scheduling this. We have p by 2 matches per day and the tournament can be completed in p minus 1 days. If so, there are 10 teams. If we have no idea about these teams and all, every one day, one match like that, only one team will be playing like that. It will be taking to 10 into 9 by 2, 45 days. If we are planning like this, we can take it in 9 days itself. We can complete the first round in 9 days. So if it was odd, then we can find easily. But two teams, we can find some matches. Then if it is if it was even, then we can find like this, either like this or something, or like this and all. Even suppose it was odd, on team will have to sit out every day. If A, B, C, D, and E. If A, E are playing and B, C, then D will have to sit out. Else like this, then E will have to sit out. Okay. Then in this case, we'll put an imaginary team. Same thing that we have done with even number of teams. When there's odd team is there, we will be giving an imaginary team. And usually it is in terms of gaming and all, it is called by team. The tournament is represented, then it is, so we have P teams, which is odd, and we are considering some other imaginary team by team, and then it is being added to this team. So if there were P teams, then this includes, including this P by team, it will be taken to P plus 1 teams. Then one factorization corresponds to the complete graph of this thing, P plus 1 teams. Again, we know that now it is P plus 1, where we know K to P has a on factorization. Now this P, which was odd, has been converted to even. Then we find the non-factorization of this complete graph and scheduling the tournament rounds. The tournament can be completed in P days. Earlier we have seen that if it, this P was even, then we found that it can be completed in P minus 1 days, and this one team extra is coming here, so we can complete it in P days. And I hope this you found this factorization okay. That is, we are decomposing a given graph into certain subgraphs of G, such that all the vertices, it is a spanning subgraph and having the vertices having certain properties. It is for this, it is mainly depending on the degrees of the subgraphs. And so it is called R factorable or R factors of that graph. For factorization or concepts, we require these subgraphs, spanning subgraphs, ring sum of two graphs, and edge disjoint spanning subgraphs, matching and perfect matching. This span-matrix factors, it has been told by many mathematicians that it is not easy to find. Whether on just looking at a graph, we are not able to say whether a graph is given graph is factorable or not. So that has given the condition whether a given graph is factorable or not. That has given the condition for on factorization, factorization, and it is that then our number of odd components of G minus S is less than or equal to the cardinality of S, where S is a subset of the vertex set of G. And then Peterson's conditions, and I hope you enjoyed this session of factorization and application of this on factorization, which is most commonly used in our day-to-day life. Thank you for watching this.